In 1972, two scientists reported the discovery of a very strong magnet. Their paper said, "We found a new magnetic material, which has the highest saturation magnetization at room temperature among those of all the magnetic materials. Not only is this material one of the most magnetic objects known, it is made from two very ordinary elements, iron and nitrogen." For 40 years, people went back and forth on whether this magnetism was real. In this video, we explore the decades-long mystery of the iron nitride magnet. I want to start off with this. Why do magnets magnet? There are 5 types of magnetism known today. The one we discussed today is ferromagnetism. Ferromagnetism's fundamental observable unit is the magnetic moment. The moment derives from electrons' intrinsic spin, as well as their orbital motions around the atom nucleus. Spin, of course, being a quantized measurement of angular momentum and has nothing to do with the particle actually spinning. These magnetic moments are themselves tiny magnets. When many magnetic moments are properly aligned, they can create on net a strong magnetic field. The hard part is corralling those moments together in a way that sticks. Iron, cobalt, and nickel atoms exhibit this special quantum effect that helps align their electrons' magnetic moments into quote-unquote magnetic domains. Unfortunately, those domains are often unordered. Them pointing in different directions causes their magnetism to cancel each other out. The net is small, or zero. You can magnetize a piece of iron by bringing another magnet near it. And what happens behind the scenes is the external magnet orienting the iron's domains in such a way to create a net magnetic field. The issue is that the magnetic field is temporary. Iron's crystal structure does not make it possible to keep those domains aligned. Heat energy eventually jumbles those magnetic domains until they become unordered again. Permanent magnets are different in that their atomic structures force the moments to align in one direction and hold them there. Almost all of the most powerful permanent magnets are made from some mix of iron, nickel, or cobalt, along with a rare earth element like neodymium or samarium. In 1971, a Japanese scientist named Migaku Takahashi is doing research at his laboratory in the University of Tokyo. His research involved measuring the magnetic properties of evaporated, deposited metal films. One such method involves heating up iron in a vacuum until it vaporizes. The iron gas then travels to the target item where it condenses as a thin film. His team was not working on this randomly for academic curiosity. In the 1960s, there was a lot of industry interest in thin films of various metal elements for computer and display purposes. Working with hand-me-down vacuum equipment from the NTT laboratory, Takahashi and 2 of his student colleagues, a Mr. Hatayama and a South Korean named Mr. T.K. Kim, were experimenting with thin nickel films. At this time, it was already known that nickel can form layers of oxides in a vacuum via evaporation deposition. During the evaporation deposition process, if you lower the vacuum, then more oxygen and nitrogen atoms from the atmosphere enter into the chamber. The oxygen atoms interact with the nickel, creating a layer of nickel oxide. Nickel is ferromagnetic, but its oxide is anti-ferromagnetic. Takahashi and his team figured that the borders where these two conflicting nickel materials meet might get interesting. So they began studying these borders for weird magnetic behavior. In their experiment, they lowered a vacuum whilst depositing nickel. And as expected, as the vacuum got worse, more oxygen and other gaseous elements from the atmosphere came inside. This created more nickel oxide, which predictably made the nickel and nickel oxide thin film less magnetic. And presumably, this goes on until the net magnetism gets to zero. This was all as expected. But unexpectedly, when the deposition vacuum got to a certain level of about 2 millitorr, a level generally considered to be low, the magnetization measurement suddenly jumped high. This was very strange. Takahashi had never seen anything like it before. and he asked his grad student, Mr. Kim, to run the same experiment, but on iron. And with the iron films, Takahashi and Kim were both shocked to discover the iron magnetism level suddenly popping up at about 3 millitorr vacuum. The weirdest thing of all was the sheer strength of the material's magnetism. It had a saturation magnetism of about 1800 to 1900 Gauss, significantly higher than pure iron's 1700 Gauss. Saturation magnetism is the point where the material's magnetism is fully saturated. So, kind of like a sponge, it is the point where the material cannot get any more magnetized. The 1800 to 1900 Gauss measurement was about as high as that of iron 65 cobalt 35, then the highest magnetized permanent magnet then known. The iron films contained a mixture of plain alpha iron and a phase of iron nitride called alpha double prime Fe16N2. This name refers to a specific type of iron crystal with nitrogen atoms modifying its structure. The crazy thing is that the average magnetic moment seemed to be about 3 Bohr magneton per iron atom, far higher than ordinary iron's 2.2 Bohr magneton per atom. Imagine that. Takahashi immediately dreamt of discovering a new permanent magnet made of iron and elements from the air with no dirty and expensive cobalt necessary. But first he had to confirm this new finding. In the end, they confirmed their measurements via multiple methods and decided to publish, and it was first presented at the Physical Society of Japan in 1971 with a paper titled New Magnetic Material Having Ultra-High Magnetic Moment, coming out a year later. Soon after publication, Takahashi consulted with a leading Japanese physics theoretician about whether what he saw was possible. The theoretician, who I believe was Junjiro Kanamori, sidestepped the question, but said that the calculations felt impossible. In 1973, Takahashi visited East Germany, and a professor there asked him for the samples, saying that he could not obtain the Fe16N2 giant magnetic moment no matter what he did. The various scientists struggling to replicate this unusually high magnetism, if the Fe16N2 material, got people wondering if what Takahashi had seen and measured was actually real. Was it an error? Moreover, this crystal structure is not unknown in history. Alpha double prime Fe16N2 is made from a pair of alpha prime Fe8N, which was first discovered and written up by Kenneth Henderson Jack at the University of Cambridge in 1951. Jack and the other people who have studied these iron crystals since have never mentioned anything unusual about its magnetism. Even Takahashi's own laboratory struggled to consistently reproduce its earlier results, coming up with quote-unquote scattered data. Over the next 10 years, Takahashi lost faith in his own findings, thinking that what had happened in 1971 was a mirage. Then in the mid-1980s, Takahashi was unexpectedly approached by some scientists from Hitachi, led by a man named Sugita. Hitachi was then working on finding more powerful magnets for their hard disk drive and wand businesses. By then, the semiconductor industry had developed better tools for producing thinner films. The Hitachi team used something called molecular beam epitaxy, which evaporates iron using an electron beam. The team evaporated and deposited a thin film of iron, in the presence of nitrogen gas, onto a substrate of indium gallium arsenide. The result was a thin film about 34 nanometers thick, showing a magnetic field strength of about 2.8 to 3 Tesla. This translates to an average magnetic moment of 3.2 to 3.5 Bohr magneton per atom. Again, regular iron's measure was 2.2 Bohr magneton per atom. In 1991, the Hitachi team published their results, setting off a massive stir in the community. But again, teams struggled to consistently reproduce these results. Occasional reports of 3 Bohr magneton were seen, but could not be consistently replicated. The community even set up 2 symposiums specifically to explore iron nitride magnetism at the proceedings of the annual conference on magnetism and magnetic materials in 1994 and late 1995. Despite this, no specific conclusion could be reached. Results remain scattershot, and standard quantitative physics models like local spin density approximation failed to predict this unusual magnetic result. Research interest soon faded again, and the 2000s saw another winter in iron nitride magnets. Then, in 2010, a team at the University of Minnesota, led by Professor Jianping Wang, published a theory. Wang was born in mainland China and did his postdoc in Singapore. In 2002, he moved to the United States and spent the next 8 years studying iron nitride magnets, trying to come up with a theory behind its quirky behavior. In 2010, he published a theory that he called cluster plus atom. The name sounds like a fancy bistro in San Francisco that sells a $15 Brussels sprouts appetizer. Anyway, what does it say? We will break it down a bit later in the video. This paper's publication had fortuitous timing. That same year, the People's Republic of China quietly, but very surely, banned rare earth exports to Japan due to a territorial dispute. People's eyes were suddenly opened to the fact that rare earth-based permanent magnets like neodymium iron boron have few, if any, peers in industry, and that China suddenly makes and processes virtually all of these rare earths. Professor Wang went to publish more papers on his theory, and more critically, pioneered a method to actually make these iron nitride magnets. In 2013, he founded, with US government funding, a startup called Niron Magnetics to commercialize the magnet. They remain one of the leaders in the space today. So, what do we know about how these iron nitride magnets work? Let us revisit the cluster plus atom theory that I briefly mentioned earlier. The first thing to know is that the iron nitride magnet is still a soft iron ferromagnet. The nitrogen atoms are not creating some fundamentally different magnet, but it does rejigger the flows in an interesting way. In ordinary metal iron, the electrons spread themselves out and travel evenly throughout the crystal lattice. Imagine it as kind of like an office building with an open layout, with various employees walking around freely inside. We established earlier that the net magnetic field depends on how these electrons are organized. In this case, this fluid-ish behavior creates a net magnetism that is strong, but not absurdly so. With alpha double prime Fe16N2, we add nitrogen into the crystal structure. Nitrogen atoms are small. Cluster plus atom theory posits that when these nitrogen atoms get jammed in between the iron atoms, they create unique octahedral clusters inside the crystal lattice. So going back to our metaphor of the overall iron crystal lattice being an open office, you might want to imagine the nitrogen atoms as creating small offices, small rooms, inside the open office plan. Inside the nitrogen cluster, electrons act differently, just like how workers act differently inside meeting rooms as compared to when they are out in the open. So in the cluster, electrons become more subject to a quantum principle known as Hund's rule. Hund's rule specifies how multiple electrons interact when traveling about an atom. In this situation, it organizes the electrons such that they create stronger magnetic moments. However, the cluster magnetic moments are not enough. They must still be collectively organized to create the crystal's big moment. That is done by the remaining iron atoms outside the clusters. They flow between those nitrogen clusters, acting like a sort of a roaming glue. You might imagine like office workers physically traveling between meeting rooms, coordinating things. So there you have it. Cluster plus atom theory posits that alpha double prime Fe16N2's unusually high magnetism stems from its unusual combination of electrons, some bound, localized, and others freely wandering. For evidence, Professor Wang and his team point to 2 instrument measurements, the first being an X-ray based chemical tool called the X-ray magnetic circular dichroism, or XMCD. This tool looks at and measures a chemical's magnetic properties. XMCD measurements show the iron nitride magnet having two different fingerprints, hinting at its dual nature. The second tool is another spectroscopy measurement called the Polarization-Dependent X-ray Near-Edge Spectroscopy, or XANES. When pointed at different parts of the crystal, XANES can compare the behaviors of iron atoms near and far away from the nitrogen clusters. And indeed, iron atoms near the nitrogen are trapped, like how predicted by cluster plus atom. As for why people have struggled to consistently recreate these giant magnetic moments, it is because the cluster plus atom state is extremely delicate. It requires that the iron crystal be strained, where the atoms are literally stretched apart. I've discussed this before in prior semiconductor videos. Strain allows the free electrons to properly travel about, and is a key ingredient in making Fe16N2's results consistent. Whenever iron nitride magnets have popped up in media, it's been as this environmentally friendly replacement for rare earth permanent magnets. People tend to focus on the upsides and the tantalizing potential, spending less time on the weaknesses. Unfortunately, there are many. First and foremost, Fe16N2 lacks coercivity. Anyone who cites the material's pure saturation magnetization numbers and nothing else is being misleading. Even regular iron has high saturation magnetization numbers. A permanent magnet must also stay magnetized when exposed to an opposing magnetic force or even its own internal magnetic field. It is literally in the job description, permanent. Iron nitride, unfortunately, is very easily demagnetized, its single greatest weakness and a fundamental shortcoming. Neodymium iron boron magnets have a coercivity of 10 kilo-Ørsted, or higher. Ørsted being how strong an opposing magnetic field needs to be to reverse the magnet. Iron nitride, by comparison, ranges from 1.29 to 3 kilo-Ørsted, depending on the magnet's physical form. Small particles coated with other materials tend to do better. The second major weakness is that the crystal structure is unstable. Fe16N2 decomposes at temperatures of about 200 to 500 Celsius into ordinary iron and Fe8N. Its magnetism power also starts degrading far before that. This is a major challenge that precludes use in many, though not all, industry settings, like EVs, turbines, and such. The best way, it seems, to deal with this is to alloy the magnet with a third element, like vanadium, but that is not a clear solution. The third tricky thing is that this stuff is hard to make. They've been trying to do it for 40 years. The cluster plus atom theory has given some insight, informing people about the importance of achieving lattice strain via deposition, but nevertheless it still requires complex processes like nitrogenation, which is where we stuff the nitrogen atoms into the iron lattice like feathers into a pillow. For this reason, the goal of getting this big block of iron nitride magnet, like we can with the neodymium iron boron permanent magnets, remains somewhat elusive. Since its founding, Niron has collected investments from big partners like GM, Stellantis, Western Digital, Samsung, and Volvo. They're working on building a U.S. factory that relies on Minnesota's iron deposits with annual capacity of about 1,500 tons of magnets. There's not a lot of documentation about what their magnets are specifically made from or how they perform, which I guess makes sense considering how common these elements are. The magnetic community seems to largely agree that iron nitride magnets are real, but push back on them being called game-changing. A 2025 paper by Mats Durba and John Ormerod, sorry if I mess up your names, of JOC LLC, published in the Magnetic Society, notes that what has been seen implies that these magnets have commercial value, but largely in niche applications that do not require high heat or coercivity, like stereo speakers. Their commercial potential is like that of upscaled Alnico magnets, these long-existing magnets made from aluminium, nickel, and cobalt. Valuable market, but nothing like the neodymium iron boron magnets that everyone is focused on about right now. And there are other rare earth-free magnet candidates out there, like the iron cobalt or iron phosphide alloys, or my personal favorite, tetrataenite. It was discovered in meteorites, where it is cooled over the span of millions of years. We shall see what those guys, or Niron, or all the other iron nitride startups eventually bring out, not to mention what all the AI science startups are cooking up right now. The search for true rare earth-free permanent magnet continues. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon. I'll see you guys next time.